Can you guys hear my voice?
Yes, sir.
All right. So we'll start now. Okay. So for an incompressible flow, if local area velocity decreases, then the dynamic pressure will. I mean, the answer is decrease, but
Sir, that is what I was getting doubt, sir. Because if the velocity decreases, then pressure decreases, right, sir?
right.
Here I use Bernoulli's theorem for pressure, sir, but still they gave answer as decreases. I didn't understand why, sir.
Okay, we'll try to explain. If anyone can answer Achyut's question. Can anyone answer Achyut's question? Okay. So yeah, maybe I'll try to explain. Achyut, what is dynamic pressure, first of all? Hello?
Sir,
Yeah, what is dynamic pressure?
sir, the pressure which varies with time.
Ah, okay. Can anyone else answer what is dynamic pressure? One name I can see is Erini, Iram, Jessica. Can anyone of you tell me what is dynamic pressure apart from Achyut? Okay. So Achyut, dynamic pressure, you took it literally, right? You took it literally in the sense dynamic means something that changes with time, right? But actually dynamic pressure is defined like this: half of rho v square. So you told me about the Bernoulli's equation that you tried to use. So let's see the Bernoulli's equation first. P plus half of rho v square. If there is incompressible flow, this number will remain constant. This is pressure and this is dynamic pressure. So this entire term is called dynamic pressure. And you are being asked if velocity goes down, then obviously the dynamic pressure will go down. Do you understand, Achyut?
Sir, understood, sir.
Yeah. Okay. Now we can probably go to the next question. Here are all drawings. Wave drag is produced due to. Answers are incompressible flow, fluid is not compressible, shock wave formation, flow separation of incompressible flow. So the answer is given as shock wave formation, and the question is wave drag is produced due to. So anyone would like to answer what wave drag is?
Sir, can I say?
Yeah, sure.
Sir, here the wave drag means that when an aircraft goes in max speed, on max speed, sir, it starts forming shock waves, sir. Those waves, when they interact with the aircraft or the body, they result in the drag, result in producing drag, sir.
Okay. And when do shock waves are formed?
When a body flow, when a body flies more than the speed of sound.
Okay, right. So because it's a direct connected with the wave drag and it's because of the shock wave. So I don't think I need to explain anything here. If someone needs explanation, they can ask me. The next question is supercritical aerofoil is primarily used for, and the answer is higher divergence Mach number. So first of all, I want to understand what is Mach number. Then I want to understand what is divergence Mach number, and then I want to understand how supercritical aerofoil is going to make how supercritical airfoil is going to make sure increase in divergence Mach number, because the answer is given. So I will discuss the answer and the other options also. But first, let's understand what is Mach number. Anyone would like to volunteer what is a Mach number?
Sir, me.
Yeah, go ahead.
Sir, Mach number means the velocity of the aircraft with respect to air.
No.
Or can we say, sir, velocity of the aircraft by the velocity of sound gives Mach number?
Yeah, that's correct answer. So Mach number is usually defined as Mach number is usually defined as the local velocity, anything that is flying with velocity v, and then not just flying. A flow might be flowing with a velocity v locally, and the local speed of sound. And I'm enforcing the word local deliberately because you can take the speed of sound on Earth, like let's say on the ground, and you're measuring Mach number at a certain altitude, let's say 2 kilometers. So you have to use a speed of sound that is at the 2 kilometer altitude along with the velocity. So both things have to be local. Local velocity divided by local speed of sound, right? And that is what you call a Mach number. Now, how can you find out the Mach number? Sorry, the speed of sound. At a given point in atmosphere, if I ask you what is the speed of sound at that point, what is the mechanism that you know that you can find out this number A? Do you know any method? No idea? So you can find out the Mach number, sorry, the speed of sound at that point using gamma RT. R is the gas constant, T is the temperature, local temperature at that point, and gamma is the ratio of Cp and Ce. These are two numbers that are used for gas. So that's how you can find uh, speed of sound, ultimately Mach number. Now we understand what Mach number is. Now, what is divergence Mach number? And we are talking in the context of airfoils. So we are definitely talking about the flow over airfoils. And in that situation, we are talking about divergence Mach number. Right?
Yes, sir.
Yeah. So I'll show you one graph and then you'll probably understand what we mean. So I'll stop sharing and share the entire screen. So now I think I've shared my entire screen and I have this. So yes, right. So now you can see the slides, right? What is this? Is CD naught. We call it profile drag, CD naught, and this is the overall CD. Okay. Now what happens is this CD varies like this when we increase the Mach number of the incoming flow. So this is the incoming flow Mach number, and this is the CD that is experienced by the airfoil. So this is the CD of the airfoil. And this is incoming Mach number. So as you increase the incoming Mach number, at some point you find out that the number is critical Mach number. And that definition of the critical Mach number is that for which Mach number, which is obviously less than Mach 1, Mach 1 is somewhere here, and a Mach number that is less than 1, and for that Mach number, flow on the airfoil is producing a Mach number greater than 1. So you clearly see the distribution of Mach numbers here. Here Mach number is less than 1, and as the flow goes on the surface of this airfoil, it becomes supersonic. So for the incoming Mach number, the minimum value of this Mach number for which the flow becomes supersonic on the airfoil is called as critical Mach number. But the drag hasn't increased much for the critical airfoil. But as you go beyond the critical Mach number, you keep increasing this incoming flow speed. At some point, what happens is this drag starts to increase and increase rapidly. This phenomena is called divergence. Divergence is called Divergence is the name of this phenomena, and particularly it's called drag divergence due to uh, speed of whenever the speed approaches Mach 1, uh, drag increases very rapidly, and this phenomena is known as drag divergence. And in that particular question, it says supercritical aerofoil is primarily used for higher divergence Mach number. So now you understand what is divergence Mach number. Now supercritical airfoils will make sure that you can use these airfoils for uh, for higher drag divergence Mach numbers. Okay. There is one more slide that I want to show in this particular example. Yeah. So what happens is, this is a normal airfoil, NACA 64 series airfoil, and this is a supercritical airfoil. Now, when the incoming flow is in critical situation, if the flow is critical, the Mach number is critical, which is incoming, the shock wave that is formed on top of the wing is relatively strong. It's a strong shock here. And when we use a supercritical airfoil, the shock is relatively weak. Okay. So this is the advantage of a supercritical airfoil, that you can use it for a Mach number that is high. And drag divergence Mach number means nothing, but I showed you in this graph a Mach number that is relatively higher than the critical Mach number. Okay. So this answers your question. Which of the techniques is employed to delay the critical Mach number? So there's a list of things, but the answer is swept wing. Anyone would?
Isn't increasing the thickness of aerofoil also correct, sir?
Increasing the thickness of the airfoil, what it is going to cause?
Sir, sorry, I got confused with
Yeah.
the fuselage, sir, because if we increase the T by C ratio of fuselage, then we can decrease the Mach critical number.
Yeah. So whenever you increase the thickness of the airfoil, you are actually reducing the critical Mach number, right? The flow will become supersonic early when there is a thick airfoil. So we use thin airfoils for high-speed applications. That is the reason, right? Achal, will you prefer a thick airfoil or a thin airfoil for high-speed applications?
Sir, thinner one, sir.
Very good. But now, since the thickness must be reduced, so the first option is wrong. But we know the right answer is swept wing in this set of four. Now, would anyone like to answer why swept wing is used to
Yes,
delay
sir.
the?
Sir, can I answer?
Yeah.
Sir, swept wing generally breaks down the flow into two directions, chordwise and spanwise flow. So
Hmm.
the main drag is due to the, we can say, chordwise flow, and main lift is due to chordwise flow. So as it divides into components, the chordwise flow decreases, and hence we can say it can reach higher critical Mach number.
Did you understand, Achal? We couldn't hear you actually. Like I couldn't hear you.
Sir, I understood a bit, sir.
A bit, okay. So the remaining bit, I'll show you a photograph and then we'll understand. Now you can see the photograph, right?
Yes, sir.
So I'll ask you, what is V naught? What is V naught?
Uh, Sir, speed of the wind.
Free stream Mach number, free stream velocity, we can.
You can say that it is the velocity, the relative velocity at which the aircraft is flying. So this is the velocity of air that is approaching the aircraft, right? Now this planform is a swept back wing planform, and this angle is lambda. This angle that is given is lambda. I don't know why they write lambda like this, but I write lambda like this. So this angle is the lambda. Now this V naught can be decomposed into two parts. One this way, and the other perpendicular to this. Now, which of these two is responsible for generation of the lift primarily?
Sir, the one which is going towards the root.
Yeah. And what is the name of this? Ripinder just named it. Both of these flow have some name. Ripinder, can you answer?
Yes, sir, this is a chordwise flow, sir.
Yeah. So this is code-wise flow. Why? Because the airfoil codes are like this. I mean, if there are airfoils underneath this wing, those airfoils are like this. Okay. That's why it's a code-wise flow. So this flow is responsible for generation of the lift. Now this is the total velocity that is incoming, but the chord-wise flow is only V naught. How much is this? Cos lambda, right? So lambda is usually, let's say, maybe 20 degrees. So you have only a part of the flow that is going chord-wise, and that is why you have a higher V naught, and still you are not going supersonic on the wing. So sweeping back the wing delays the what you call uh, supersonic flow on the
Shockwave
yeah
development of the supersonic flow over the aerofoil.
yeah. So supersonic flow or shockwave formation on the wing, you delay it. Okay, so that is the answer. Now we go back to the questions.
Sir, sir,
Yeah.
just a second, sir. Sir, I always have a question in mind
Uh-huh.
that in a setback wing there is spanwise flow. So, sir, won't this
Right.
spanwise flow be increasing the vortices and increasing the induced drag
Okay, but how? Let's
due to
let's try
spanwise flow? Yes.
let's try to understand. Okay, so this is the span-wise flow, and you're saying
Yes, sir.
that it will cause what?
Contribute to the formation of more vortices at the tip.
More vortices. Now we are looking the wings from the top, and what is the direction of the flow from the vortices? Let's say this is the
Yes, the
bottom of the
bottom
wing.
ఇది ఈరోజు పాసెస్ తీసుకున్నాము. నేను 400కి
Sir,
పైసలు ఏడరా రేపు రా.
Can-
అప్పుడే నువ్వు ఎన్సీసీకి వెళ్ళిపోతున్నావు
sir,
కదా.
Jessica, your
someone mic
mic
is
is
అప్పుడు అప్పుడు తీసుకోలేదు. ఇప్పుడు ఈ మధ్యాహ్నము వర్క్ షాప్ అయిపోయినాక నువ్వు
how
వెళ్ళిపోతున్నావు
can
చూడు
how can we make
ఎన్సీసీకి. అప్పుడు తీసుకున్నాం
that
జగన్
mute?
ఉండని. రేపు ఇస్తాడంటారా 400కి. రేపు రేపు ఇస్తాడు. రేపు కొట్టు.
Because I'm not the host of this.
ఏంటి
He has no idea.
అంత లేవు వాళ్ళ దగ్గర చాలా ఉన్నాయి. మేము చెప్పినాం కూడా రేపు ఇంకా 3 తీసుకుంటామంటే సరే అన్నాడు. వాడు
yes, sir.
అన్నాడు
He has no heart.
ఓన్లీ నేను మ్యాగీ కుషాల్ తీసుకున్నాం అంతే. కుషాల్ ఇంకా కొట్టిండో లేదో తెలియదు. ఇంటికి వెళ్ళా కొడతా అన్నాడు. మన ఇది కొట్టిండో లేదో మరి. పాలు తీసుకున్నాడు. కొట్లే ఏమో కొట్టాలి. వాడు ఈ రోజు కొట్టినా మరి రేపు కొడతాడు.
I think I have to ask
ఇంకా
these
వాడి దగ్గర
people
చాలా
to provide
ఉన్నాయంటారా.
me
5 తీసుకుంటే 400కి ఇస్తాను. నేను 400 నేను
the
400
host
అడిగిన అందరు
responsibility
400
because
ఇవ్వాలి.
they
ఇంకా
have
సరే
created
అన్నారు.
the
సో
link
అందరు 400
for
ఇచ్చిండు.
us and we only joined.
అది
So,
వేరే 400 కొడితే
can you hear us,
పాస్ ఇస్తాడు.
Jessica?
లంచ్ బ్రేక్ లో ఉంటావు కదా వాడు ఇస్తాడు. వాడి దగ్గర ఉన్నాయి, చాలా ఉన్నాయి వాడి దగ్గర. ఇప్పటికే 100 పాసెస్ తీసుకున్నారంటారా. 10,000 అంట. వాడికి ఇచ్చిర్రంట పాసెస్. సో
This is pretty
అట్లా
irresponsible.
వాడు చెప్పింది. మీ ఫ్రెండ్స్ ఎవరుకున్నారో వాళ్ళందరూ చెప్పండి నా దగ్గర తీసుకోమని
Sir,
అని.
maybe you can write in chat box. Maybe
అది
she'll see it.
సో రేపు చేస్తే రేపు
Okay.
ఇస్తానంట. మేము యాక్చువల్లీ రేపే అందరు కలిసి రేపు అందరం ఉంటాం కదా. రేపు అందరం కలిసి ఇద్దామని. మ్యాగీ ఏమో పైసలు మిగులుతాయి తిందాం అన్నది. అందుకనే 100 రూపాయలు మిగులుతాయి కదరా. 500 కాకుండా వీడి దగ్గర 400 తీసుకున్నాం కదా. సో అట్లా అది రేపు తీసుకురా. రైట్ బాయ్.
Sir, I guess she's on a call and the mic is
Jessica, can
on.
you hear us? Your mic is unmute. Now she has muted. All right. So basically, you have disturbed us for like 5 minutes, and you did not know you were on a call, and we were hearing you. All right. Keep in mind that you mute your mic. All right. So we were talking about
What is formation, sir?
yeah. So the flow when vortices are formed is like this,
Yes, sir. From downward. Yes.
and the span-wise flow is like this. So isn't it trying to destroy the vortices? This span-wise
Sir,
flow.
it is from top, sir, but from bottom we can also say that the same now. That the spanwise flow is contributing to the from the downward to upwash.
Okay, but which one is higher?
Sir,
The flow on the
it
top
is
surface or
equal.
the flow on the bottom surface?
Sir, I think higher pressure is on the lower side. So higher pressure will try to come to upward.
That's okay. But what I'm saying is, when the flow goes at the bottom of the this incoming flow, so the distribution is not going to be uniform,
Okay, sir.
right?
So, sir,
But
you mean the both spanwise flows from upward and downward are equal. So they both cancel out each other. Sir, I couldn't hear you. Can anyone else hear, sir?
No, even I'm
Ah,
not able to
sir
hear.
left the. Sir left the. Maybe his connection was off.
I lost my network connection, and that's why I went out of the meeting.
Yes, sir. Yes.
Yeah, now I'm back. Okay. So what were we saying?
Sir,
We were talking that the flow on the top surface and the bottom surface, you said that they will be uniform, like they will be equal and they will cancel each other, right? The impact of each other.
yes, sir. This could also happen.
Yeah. So maybe it's partly true, maybe, but I'm uncertain that the flow on the top surface and the flow on the bottom surface will be essentially equal. Partly they will be equal, but the surfaces, the interaction with the top surface and the interaction with the bottom surfaces are different. All right, and
Yes,
that
sir.
is why I believe the flow on the bottom surface, maybe it's span wise or maybe it's chord wise, it's going to be slower than the flow on the top surface. The flow on the top surface is at higher speeds. Now that can be actually simulated in maybe some software, but I have this feeling that the flow on top surface will be slightly higher, and that will actually contribute to reduction of the vortices instead of its generation. So usually that's why we don't study that there is any adverse effect of the sweep on the generation of vortices. I mean, I have never encountered any study that claims that this
What is
yeah,
degeneration
yeah,
due
yeah,
to spinal flow? What
yes,
is
yes. It most probably impacts positively because of the higher speeds on the top surface. Okay.
Yes, I got it.
Yeah. Okay. We are at the fifth question. What is relation between drag divergence Mach number and critical Mach number? Achyut, can you answer?
Sir, actually, I got this answer wrong, sir. I kept Mach divergence number is equals to Mach critical, sir.
What do you think, Ripinda?
The Mach divergence Mach number is always greater than the M critical Mach number, because
Mm,
at M critical, the M divergence, drag divergence Mach number, drag suddenly shoots up exponentially up to 10 times or more
right,
because of heavy normal shock wave formation on the upper surface,
right.
which is obviously at higher than M critical.
And how is M drag divergence is related to M is equal to 1? Did you understand my question?
Actually, not, sir.
How, like, is it larger than Mach equal to 1 or is it smaller than Mach equal to 1?
No,
The
sir.
M.
It is
Uh,
larger
it is,
than one, sir.
Hmm?
sir. According to me, it is less than one, but very close to one.
Yeah, that's the right answer. It's very close to 1, but it's still less than 1. And what happens at 1? I mean, this,
So I think there is a formation of the upper and lower shock waves on both edges of the tip of the aerofoil, trailing edge,
mhm,
and maybe in the transonic region 1.1 to 1.2 max, there is a bow shock wave ahead of the aerofoil as well.
right. So I showed a photograph earlier also. I'll show it again. This is a photograph, and see, this is a plot of drag coefficient CD when we increase the Mach number. So we clearly see that for until Mach critical, CD doesn't change significantly. It's almost constant. But after Mach critical, it starts to increase. Now, which number is drag divergence Mach number? I mean, definitely A, B, and C are not,
E
but
is, sir. E it is.
E. So D, E, F, G, and H, right? So one answer is E. Why?
Because the drag is increasing exponentially now from point E.
Okay, and why not F?
So it is somewhere between, like, drag is already very high up, and
Mhm.
without any significant increase in the M infinity.
Okay, so let's say no, my question is actually on the definition of drag divergence Mach number. I understand that it is going to be a Mach number that is greater than MCR and less than 1, and this is the region where there is an exponential growth in CD. But the question is it D or is it E or something close to E? How to define that number? I mean, I give you this curve, so you should be able to pull that number out of this graph. I mean, that is the question.
Yes, sir, I can, sir. From the point E, sir, I can see
No,
it.
no, 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 no. My question is, what is the definition of point E?
Sir, it is the value of the Mach number at which drag is increasing exponentially. So we can see that, like, from D onwards, still not, but from E onwards, drag is increasing very rapidly.
No, that we can see qualitatively. But let's say, let me make it more specific. My question is slightly different than what you're answering. What you're answering is absolutely correct. I have no dispute with that. But my question is, let's say I compute the slope dCd over dm. So slope here and a slope here and a slope here. So I can clearly see the slope at F is the highest
Yes,
and
sir.
slope at D is a little smaller than E. Okay. But the question is, how do I choose this slope? Okay. We're both saying that it exponentially increases. Exponentially is sort of qualitative word here, not exact exponential. Let's say it's not like e to the power m, something like that, right? Let's say some coefficient lambda e to the power m. So it's not definitely like this. It's something, some combination of exponentials, okay, probably. But the question is, which slope would you choose? I mean, which slope would you, because all of them are increasing now. One is smaller, one is greater, but which one? I mean, that's a question to all of you.
Yes, it is
I
a tricky question, sir.
Yeah, I have hidden it, and I need this answer in the next session. Which one? Okay. You can take the screenshot of this photograph and just explain to me why. Okay. All right. We go back to the sixth question is, what is the thickness of NACA 0002 airfoil? Answer is 2%, but what is the explanation behind that?
So the designation of the NACA four-digit series is that the last two digits will give the thickness of the maximum thickness of the aerofoil in percentage of chord.
Right.
So the last two digits are 0 and 2. So we can say that it is 2% of the chord.
Yeah. Now you have used the term like 4-digit airfoil. So I hope that everybody is understanding 4-digit airfoil. If they don't understand, Ripinda, would you like to explain what all four numbers mean?
Yes, sir.
Yeah, go ahead.
Sir, so the first digit will tell the percentage of camber, I guess.
Camber
First,
or maximum camber?
maximum camber. First
Yeah.
digit, maximum camber. And
Mm,
second, denotes the location of the maximum camber in terms of chord.
mm, mm.
And the last two are the thickness of the maximum thickness of the chord, of the aerofoil, um, in percent of chord.
Okay. So let's test other people. Ripinda, you will keep quiet and I'll test other people just so that everybody is on the same page.
Sure, sir.
2, 4, 1, 2. Now, apart from Ripinder, I want to know explanation behind these numbers. So this is one airfoil NACA 2412, and now you people will tell me what these numbers mean.
Sir, can I say?
Yes, go ahead.
Sir, the number 2 represents the maximum camber present, sir.
So 2 centimeter is the camber or what? Or 20 centimeter, maybe.
No, sir.
So what is
It is 2% of the camber, sir. That means 0.02 percent of means 0.02 of chord
okay?
length, sir.
Let me make life simpler for you. The chord is 100 centimeter. Now tell me what is the maximum camber. Achoo?
Yes, sir.
Now for 100 centimeter of chord, what is camber?
Sir, it is 2, sir. 2
2 what?
centimeter.
Very good, 2 centimeters. So you can say it's a 2% of the chord, right? And
Yes,
it
sir.
will be 0.02 times the length of C. So C is 100, that's why 2 centimeter. Okay, so 2 is clear, it's maximum camber. How about 4?
Sir, it is the maximum camber present from the leading edge, sir.
I mean, maximum camber was 2 centimeter, right? So now what is this? Anyone else? Harini, Jessica? Dipinder, will you answer what is 4?
Sir, it means the maximum thickness present of the maximum thickness present in that aerofoil from the will be the distance of 0.4 C from the leading edge, sir.
Okay, so for
Just 2
100
words more, sir. Just 2 words more. Location of maximum.
yeah. Okay, so let's say Achuk, 100 centimeter is the chord length. Now tell me how many centimeters is your location of maximum camber is, because it is the location of the maximum camber from leading edge. Okay, so for 100 centimeter, what will be the length? You just told the answer, but you're not confident. Okay, so I'll tell you again. It's 0.4 C. So C is what? 100 centimeter. So it's 40 centimeter from the
40 centimeters, yes.
leading edge. And the last 2 digits are the
T by C ratio.
what is the last 2 digits?
Sir, the maximum thickness to chord
Yeah.
ratio is present.
Right. So it is basically 0.12 times C. So if your C is 100, in that case, it will be 12 centimeters. All right. So in this case, you see the last 2 digits are 02, and that's why 2%. Okay. Let's move ahead. What is generally given in a swept back wing to avoid tip stall?
Yes, a washout is that.
Okay. But now, maybe if all people are familiar with the terms washing, washout, flap, uh, you would like to volunteer, Ripinder, for explaining what is washing,
Yes,
washout?
sir.
Go ahead.
Sir, so washout is the twist given to the airplane in which the root incidence is greater than the tip incidence.
Hmm.
And washing is just opposite of that, that the root is at a less incidence than the tip incidence angle of attack.
And how about flap?
Sir, flaps are at the trailing edge. We can't say that
Yeah, they're not
it
directly
is
related
for
to.
tip stall. It is just to increase the maximum CL.
Exactly. So my question to everybody else apart from Ripinder, did you understand what washout is
Yes,
and
sir.
washing? Okay. Now I want to understand in Achyut words. What do you understand by washout?
Sir, washout is generally done to uh, increase this stall, sir, because um, if we keep a swept wing, sir, when the aircraft will be flying, it will lead to tip stall, sir. To avoid that tip stalling, a twist is done to increase the stalling angle, sir, which is known as washout.
Okay. And what do you mean by twist?
Sir, it means a little bit bending of the tip of the wing, sir.
Yeah, you are right. Okay, I'll show you one photograph that will explain you maybe more clearly. Which one is that photograph? Yeah, this one. Okay. Now there is the word incidence. What is incidence? High angle of incidence, not
So we
attack.
can say the angle of attack with respect to velocity or with respect to fuselage or fuselage reference line.
Yeah, it's an angle with respect to fuselage reference line. Because if the aircraft is not flying, we don't really know which way the wind is coming, right? So it's the angle with respect to fuselage reference line. All right. And the idea is that this angle is higher uh, at the root and gradually becomes smaller. So there is a twist in this wing and low angle of attack at the tip. So what is the advantage of low angle of attack at the tip, Achut? Low angle
Sir,
of incidence.
sir, it will lead to higher star angle, sir.
Do you agree, Pinder?
No, sir. Actually, it is to demode stall.
Okay. So Achut, do you want to induce stall or do you want to reduce the stall or mm, you want to make sure that stall is not occurred, is not caused?
Sir, I want that stall doesn't occur, sir.
Stall doesn't occur. That's what you want, right?
Yes, sir.
So if your angle of incidence is low, which means you are probably operating here for this section. For this section, which is at the root, you might be operating maybe here. And this is angle of attack, and this is CL. I didn't name it. So where do you want to operate for the tip? You want to operate close to, I mean, smaller angle of attacks, right? You want to operate in this domain. If you're operating in this domain, even if the angle of attack is changed, I mean, because of the vortice is by some large magnitude, let's say by this magnitude, you're still safe. You're not causing the stall. Stall happens here, right? And what is the definition of stall, Achit, if you know? Where does the stall occurs in this graph and how do you identify that stall? You want to answer, repeat that. How do you identify stall in
Yes,
CL
sir.
alpha graph?
If there is sudden loss of lift or in CL max after a certain angle of attack.
Some loss of lift, right? Okay. So how do you identify that point in this graph? Uh, where is that graph? How do you identify the stall point in this graph? This is CL and this is alpha.
Sir, from the point where the graph shows a fall, and we can
Graph
say
shows
alpha
alpha.
stall is the peak of the graph.
And okay, I agree. You can say mathematically that wherever DCL over D alpha becomes 0, after that point, stall is going to happen, right? So this is the point where there is zero slope. So CL alpha is equal to 0. That's a warning for you that you should not increase alpha beyond this point. So this is the point of stall. Okay. Point of maximum lift coefficient is also the warning for stall. Okay. We'll go ahead. We have had enough discussion. Yeah. So this is called washout, and the opposite phenomena will be known as wash in which the incidence angle will be smaller here and higher here. I mean, do you guys know anything where washing is used? Any device, let's say, or element, aerodynamic element, where you use the phenomena washing?
Tail.
Tail. I mean, tail is
Or the horizontal stabilizers. So I mean,
why? What advantage it will offer there? I don't know. Maybe, but I'm not sure if it's used there.
Sir, actually, I haven't as well didn't see any example in which washing is used.
Okay, so
I
here is a
have maybe I have read somewhere that in some war planes in World War II they have used, not in all planes, just in one or two
okay.
experimental planes. I have read
Okay,
that.
so because Ripinter and Achyut and Achilles, what's your name? I couldn't see your name again. Akhileshwar, yeah. So I have been seeing that you three people join regularly. So this is an assignment for you people. Again, I'll mention. Okay. The first is identify the drag divergence Mach number. How do you identify that? First question. So it's an assignment I'll ask you people in the next session. And the second number is, can you give me an example where washing is used as an advantage? And maybe a hint for you, maybe you can look for propeller, how the twist in the propeller changes and what's the twist at the root and twist at the tip
Yes,
of
sir,
a
I have
propeller.
seen this, sir. In
Okay.
a propeller, yes, sir.
Yeah.
It is
So
more twisted at the root and less twisted at the tips.
yeah,
But sir, isn't it washed out normal?
what did you say?
Isn't it wash out in the propeller? Like
That,
higher
that, that
speed
is the
and
question. I just gave you a hint of a device that
okay,
you
sir.
can also look at. Okay, apart
Okay.
from wings. Yeah. So we will discuss these two questions in the next session also. Now we can go ahead. What is reflexed camber airfoil? This question has appeared so many times in this. I don't know why they keep asking the same question over and over. I mean, do you guys also feel like it's a repetitive question?
Yes, sir. Two or
Yes,
three
sir.
questions are always repeated.
I think so. It has repeated in more than in two of the assignments, sir.
Yeah. So you want to discuss it or we can skip it?
Sir, we can skip it, sir,
Yeah.
because the same thing I asked you, sir.
If you
What is
say this,
reflex camber
we'll
airfoil?
skip this. And if anyone else has doubts, they can ask us. Okay. Determine the corrections or otherwise of the following assertions. The question is, most of the wings are using cambered airfoils. Cambered airfoils can produce positive lift at 0 degree angle of attack.
Sir, this
And
answer mine is wrong, sir. I have chosen B answer.
you've
B
chosen
option.
B option. So it says both A and are true, but R is not correct reason for A. So what was running in your mind when you thought that cambered airfoils can produce positive angle of attack? That's why we use a cambered airfoil. I mean, what was running in your mind? What were your thoughts?
Sir, I mean, it doesn't necessarily the reason for this that a camber aerofoil. Camber aerofoils are used so that they can produce a good lift.
Good lift.
Yes, sir, but not necessarily at zero angle of attack. They
Hmm.
provide a good lift at any angle of attack, like from -2 to 14-15 degrees.
Right.
They will provide better lift than a symmetrical or an negatively cambered aerofoil.
For any given angle of attack, not just zero, right?
Yes, sir. Yes.
So what is so special about zero?
Sir, like zero incidences where the aircraft is flying, we can say in cruise or normally.
Yeah, it flies close to zero, not exactly a zero.
Yes, sir.
Yeah.
2 or 3 degrees.
So, so why is it important to fly at 0 degree angle of attack or close to 0 degree angle of attack? Let's say.
Because sir, less flow separation will happen and less drag will be produced.
Oh, that is some aerodynamic argument. You can fly at higher angle of attacks also. Okay, for better efficiency, not just close to zero, right?
Yes, sir.
Yeah, but why it is preferred that commercial planes fly around 0 degree angle of attack?
For passenger comfort.
Yeah, that is the answer. Because let's say you have an inclined surface. So when the crew is providing you, let's say, food or water, they will be traveling on an incline. Do you understand it?
Yes, I got it.
Yeah. So you don't want that incline, and that's why you want to operate very close to 0 degree angle of attack. All right. So we can move ahead. For a cambered airfoil, Cm naught ACW is always negative. This question also has appeared many times, right?
Yes.
As far as I can remember, it has appeared many times, but even though I did not discuss it earlier also, so today maybe I want to discuss it. Now, question is open to all of you. Why that happens? Why is it negative? Or you can show me a derivation by sharing your screen if you want to share. Or you have any logical reason why it's negative?
Sir,
Yeah.
sir, I have studied in my stability lectures that Cm naught should be positive and Cm alpha should be negative.
Yes, right.
But sir, here it is saying Cm naught around AC of the wing. Maybe that's why it is negative.
Hmm. So here we are not ensuring stability in question 10. We are just talking about the properties of a cambered airfoil. So that is the distinction.
Okay,
Even
sir.
there is, even though we use a cambered airfoil on the wing on the aircraft, we make sure that the overall Cm naught is positive, not because of the wing only. So the
Yes,
wing
sir. Yes,
only will
you're
be
right, sir.
negative.
Got it.
Hmm. So what do we
Reflect
do to
aerofoil
make sure?
have Cm naught positive. Reflect
Right.
aerofoil.
Right. So for a reflex airfoil, you can fly wing alone configuration in stable mode. But for a cambered airfoil, you cannot fly uh, wing only configuration as stable. So what do you do? Achud, I want to hear from you. If the cambered airfoil CM naught is negative, so a wing that is made up of cambered airfoil will also have a negative CM naught, right? About AC. So how can you fly it in a stable mode? Not just stable, how can you pitch it at positive angle of attack?
So,
Akhileshwar,
Yes, sir.
how can we fly aircraft at a positive angle of attack when the CM naught is negative? So it's pitch down moment. It's generating pitch down, but you want to fly at a constant angle of attack. So how do you pitch the aircraft at a positive angle of attack when you have a negative CM naught from the wing?
So by using the flaps, I think.
But flap is part of the wing. They are generating more
Okay.
lift.
So the tail must be giving the upward nose moment
Yeah, that is
required.
the answer. That is the answer. I just wanted to hear that tail is used. So, so now you should understand that why tail is important. Okay, for a cambered airfoil, you cannot fly the aircraft in stable mode until you have a tail. Okay, and you can fly wing only configuration for reflexed airfoil because they have a positive CM naught. So this distinction you should understand. So we have 10 questions. We have completed 10 questions in 1 hour, and we can probably study something else now. So I prepared some photograph. I'll come back in 1 or 2 minutes. Okay, and you stay online and just this is a photograph for directional stability. So I'll directly come and ask the question, what is directional stability? You're free to Google. I'll just be back in 1 minute. All right. So anyone would want to answer? What is directional stability?
Sir, me.
Yeah.
Sir, it is the ability of the aircraft to yawn into the wind in order to maintain its directional equilibrium.
Absolutely correct. Does anyone have any contradiction?
No,
think
sir, I
no.
think he's correct.
Yeah, he's correct. So in this photograph, you see an airplane, and this is the x-axis that is attached to the center of gravity of this aircraft. Okay, we just choose it. This is the x-axis along the fuselage, and this is y-axis of the aircraft, and this is the direction in which the aircraft is flying currently. But the x-axis is not exactly aligned with the velocity of the aircraft, and that's why we have something called side slip. Okay, so I want to explain this angle to you, this side slip angle beta. It's an important angle. You can call it as angle of attack from the side. Okay, how do you interpret angle of attack uh, for an airfoil? You have a horizontal line, and this is air. Okay, this is velocity of the air, and you call this angle of attack. And for now, because the object is three-dimensional, there is one plane. See, there will be a z-axis also going downwards for this airplane. So the plane xz, I'm talking about the plane. So there should be a plane xz. The plane xz makes an angle beta with the velocity, net velocity vector of the uh, aircraft. Okay, so that angle is called beta. Now, when you have a side slip angle beta, we call it side slip. I don't know if you have seen this quantity earlier, but I'll still write it. So beta is equal to side slip. Okay, and let me erase it. So whenever there is a mismatch between the direction of the velocity of the aircraft and its x-axis, what is going to happen is a side slip is going to come. Now, how this aircraft is going to behave, like what will happen this point onwards? So aircraft is here at point A. If it goes ahead, let's say at point B, which way the aircraft will turn? What will the aircraft try to do now? We are looking at the aircraft from the top. So what is it going to do? Will it turn left or will it turn right? So by left, let's not talk left or right. Let's talk clockwise or counterclockwise.
Clockwise.
Clockwise. Who agrees clockwise? And who says it will rotate counterclockwise?
Sir, do you mean to say that the aircraft is at the position A and has went to B?
Yeah.
So in order
At
to
B, yeah, go ahead.
B, sir,
Hmm.
A to B.
Yeah, A to B.
So the aircraft, in order to achieve the equilibrium, it will turn in clockwise direction, sir.
In clockwise direction. And you said to attain the equilibrium. So what do you mean by equilibrium?
Sir, sir, here it might be that the aircraft wants to fly in the uh, direction A, sir, but due to some wind gust or disturbance, it was pushed to uh, direction B. So
No.
so if it wants to achieve that
What is equilibrium here,
stability.
Rupinder? Achyut said the aircraft wants to go into equilibrium, and that's why it will turn clockwise. So the question is, what is clockwise? Sorry, what is equilibrium?
So like the airplane will try to yaw to the direction or directly hitting into the wind.
Directly hitting into the wind. What does that mean?
Yes, sir. There is a we can say the beta is a side slip angle.
Mhm.
So it will be producing negative lift on the left side of the rudder of the plane, and
Mhm.
high pressure on the right side of the uh, vertical stabilizer. So
Mhm.
as it is an aerofoil, so unbalanced force are created and which
Mhm.
will help, which will try to push the aircraft into the to the direction of wind, so that the side slip angle is zero.
Yeah.
That
So that is the
equilibrium,
answer I was looking for.
yeah.
Equilibrium here is beta is equal to 0. Okay. Now you have a beta which is positive, and that positive beta should be made 0. That is what stability means, right? In directional case. So the wind velocity is coming from the direction of v. So aircraft rotates itself and aligns the x-axis with the v, making beta is equal to 0. So that beta is equal to 0 is the equilibrium point in this case. Now, Ripinder spoke something more than that, and I will try to explain what he exactly said. Uh, he said to rest of you people, he said, if there is a side slip angle, it is like an angle of attack. So wind here will be coming like this, and it's definitely an airfoil, right? It's an airfoil. It's a proper airfoil. So which way the force will be generated? Achyut will answer. Which way the force will be generated? Along, this is y-axis, this is x-axis. So this is, you can say this is positive y-axis, and that is negative y-axis. Y, but negative axis. Now the question is, Achyut, which way? There are four directions if you can look it in this page: y plus, y minus, x plus, and x minus. So x minus is that direction. The question is which way the force will be generated on uh, this airfoil, or maybe vertical stabilizer. That's a fancy name for this.
Sir, towards the negative y-axis.
Towards the negative y-axis. Okay. So Achyut is saying this way the force will be generated. Is it the only force that will be generated, or there will be other forces on it? Or is it the correct force that I made for lift? Does anyone have any?
No, sir, I think so. You have drawn that arrow, sir.
Uh-huh.
I think so. It might come along that direction, sir. It won't be able to go, but means at an obtuse angle to the to the arrow which you have drawn, sir.
Okay, so one option is this L1. Let me draw another option. And the other option is this one. Let's say, so let me call this L2, let me call it L1. And these two are at 90-degree angles. So which one is the correct option, L1 or L2?
L2, sir.
L2 is the correct option, right? Does everybody agree? Why is that?
So because the lift is perpendicular to the direction of relative wind.
Okay, so is lift the only force acting on this, or there are other forces that will also act on this vertical stabilizer? Is lift is the only force, or other
A
forces
little
will
bit
also?
of drag as well.
Yeah, because it has to. Now we can ignore that. That's a different issue. But conceptually, you should be very clear that it is exactly another wing that is standing vertical. You have an incoming flow. It will generate a lift, and that lift is going to cause a moment. Moment about which point?
CG of the aircraft.
Yes, CG of the aircraft. The rotational dynamics of the aircraft means it's rolling, pitching, yawing. All of this takes place about the CG. It's because of the way Newton's laws are applied to aircraft. Okay. So about CG, so now I can safely say that there is a component of lift. I'll call that L, just a component, but it's not exactly the net lift. But a component of lift is acting on this because of the side slip. And therefore, about this point CG, the aircraft will try to turn clockwise and make beta 0. In that case, it is a stable aircraft. Now, for a stable aircraft, which of the two curves is correct for Cn and beta? Maybe I have not explained what Cn is, but it is similar to Cm. There was a pitching moment coefficient, right? And you had a curve Cm alpha, Cm with respect to alpha. So it's a similar curve. Here alpha is replaced by beta. That is also angle of attack, but its name is side slip. And this is also moment coefficient. This is about which axis? Cm is about which axis?
Y-axis.
Very good. And Cn is about which axis?
Z axis.
Z axis, correct. Okay, so it's also moment, it is also moment. You are very familiar with this curve, Cm alpha being negative, Cm
Yes,
naught
sir.
being positive. You're very familiar with this. You study it almost every day, okay, in this course. Now tell me, that was the stable configuration for a uh, longitudinal stability. But for directional stability, which one of these two? This one, the first one, and the second one. Which one is stable?
Sir, in wing we have studied that the negative uh, C and beta should be negative.
Uh-huh.
Like in wing we have studied, so I think that the downgoing slope should be stable, but it
Uh-huh.
is written clearly unstable. I don't know the
Okay, so
reason
you
why.
have a conflict here, right?
Yes, sir.
Okay. Achyut, you have conflict here?
No, sir.
You,
Because
which one is,
here, sir, I believe in Cn beta greater than 0, sir. Because while today I was doing the vertical, means the tail selection class, sir.
Mhm,
So in there, sir was explaining that when we take Cn beta
mhm,
uh, versus Cn delta R, sir.
mhm,
So there, if Cn beta is greater than 0, the
mhm.
plane will try to attain its equilibrium. But if it's less than 0, then plane starts spinning, sir.
Okay. Okay, let's resolve this conflict. Okay. So, what is positive moment direction, Ripinder? What is a positive what do you call it? Positive yawing moment. So, what is positive yawing moment
Yawing into the from the
in
Z
this
axis,
plane?
right direction. Yawing into right.
Yawing into right is positive, right?
Yes, sir.
So for a positive beta, your aircraft should perform a should generate a positive yawing moment or negative yawing moment.
For what, sir?
For a positive side slip angle, your aircraft should generate a positive yawing moment or a negative
Positive,
yawing.
sir. Positive.
And which of these two is, so let's say the beta is somewhere here. Okay. So which of these two generates a positive moment?
Upper one, sir. Positive slope.
So which one should be stable?
Yes, sir. Positive one.
You got it now?
Yes, sir.
Yeah, it's a matter of direction. Okay. So which way the stable direction is, sorry, the positive direction is, that ensures which one is stable. All right. So we can move ahead. Probably we are clear on this page. Now we want to quantify actually how much CN will be generated, and how can you quantify this in terms of force that this vertical stabilizer is experiencing. So we'll do the similar calculations as are done for a longitudinal stability. But remember, it's what kind of airfoil is it? Is it symmetric or asymmetric
Symmetrical, sir.
or cambered? It's a symmetric airfoil, therefore it doesn't have a non-zero moment, because if you recall, uh, if it was Cm, so let's say it's passed through the origin. So is it not the desirable graph for that? The desirable graph for that is this, a positive Cm naught, because the airfoil was cambered. Even if it was not cambered, the tail will ensure that Cm naught is positive. But in this case, the Cm naught is 0. There is no need for Cm naught because it's a what you call it, symmetric airfoil. So there is no moment when beta is 0. So when beta is 0, aircraft is in equilibrium. That's why 0 moment. Okay, let's go ahead. Okay, same photograph, slightly slightly different. Anyone wants to answer what is happening in this picture? Explain what is happening in this picture.
Sir, due to side slip of the aircraft, sir,
Mhm.
the tip of the wings are producing vortex towards the horizontal tail, towards the horizontal tail of the aircraft, sir.
Also vertical because they are located in the same place, right?
Yes, sir.
Mm.
So here the aircraft, in order to achieve its equilibrium position, I think so they have placed dorsal fins to create that vortex and bring the plane into stability, sir.
Right. So you're correct. The idea is that whatever side slip the wing is experiencing, or the airplane ahead of the wing is experiencing, the side slip angle, that side slip angle is not experienced by tail. And the reason is these vortices. I mean, these vortices disturb the flow in some sense. So the angle of attack is not beta, but beta plus some sigma. Okay. So that is what's depicted here, that angle of attack at the tail is different from the actual beta. And when we quantify the force on this uh, aerodynamic surface, which is your vertical tail, you should know how much angle of attack it is experiencing. So this picture simply describes that yes, there is a side wash, and to quantify that side wash, we simply add its impact. It could be positive, negative, we don't care. It's a number for the time being. We just add it. Okay. So in the next slide, we quantify. So alpha V is basically angle of attack for the vertical tail, and angle of attack for the vertical tail is beta plus sigma. Okay. Now, apart from Achyut and Ripinder, any one of you will try to answer me what is happening in this equation here. Give me a sense of all the words, because it's very, they are written in a convenient notations. So there are different notations. Akhileshwar,
Yes, sir.
so what is N here?
And is the I think the load factor that acts upon the plane.
No. Harini?
Sir, may I?
Yeah, you will be the last one.
Okay, sir.
So, yeah. Achyut,
Sir,
what is N here?
sir, and is
Okay, here is slight hint for you, just to help you. Let's say this is the vertical tail. It's experiencing an angle of attack alpha v, which is equal to beta plus sigma alpha v. It's generating a side force that is yv. This is your center of gravity, and this length is lv. Now tell me what is nv. Ripinder.
Sir, it is a movement,
Yeah.
normal movement.
Yeah. It's a moment. Achyut, you understand what moments mean?
no, sir. Can you just explain it a bit?
Yep, definitely. So moment is basically the torque, or I only know two words, torque and moment. Sorry, I'll try to explain you what is happening here. Okay, So let's say there is a road. Imagine just a road of some thickness. You are applying certain force on it, and the road is rigidly, not rigidly, it's hinged here. So it's free to rotate in this plane. Like the road can take this place, or the road can take this place. Okay, we are pulling it with a force. Now this is the force, and this is the distance from the point about which it is free to rotate. That distance is L. So the amount of torque that this road is experiencing is quantified with multiplication of F and L. And if L was at certain direction, then you will take a component of the force which is perpendicular to this road, and you call it moment or torque. Okay, torque is, it's not usually called torque, they call it moment most of the time. Torque is usually generated because of some external factors. So yeah, now you understand
Yes, sir.
the applied force and the length from the point about which the force is trying to rotate this object. So here the object is airplane, and I'll go back to the previous picture just to explain you much clearly. Yeah, I will explain in this picture here. What is happening here? A side force is being experienced by the aircraft because of the angle of attack. Somewhere here is the CG of the aircraft. There is this length LV, the length of the aerodynamic center of the vertical tail, and this force Y is acting on the aerodynamic center. So how much moment, and that moment is represented by N. There are three moments, L, M, N. L is about X axis, M is about which axis? Y, and N is about Z axis. So it's a convenient notation for aircraft dynamics community. Whenever they see L, they simply assume that it's a rolling moment, it's a pitching moment, it's a yawing moment. So in this case, it's about Z, that's why N. So that's a convenient notation that's used in aircraft community. All right. Yeah. So this is the directional moment or the yawing moment, and LV is that length, YV is the force. So how do we expand YV? LV is right here. This is the expansion of the force. Now, anyone wants to explain what just happened here? How can we write YV as this long expression in terms of some CL alpha V, beta plus sigma, QV, SV? What is happening here?
Sir, can I say?
Yeah.
Sir, YV is the lift created due to the side slip angle
Mhm.
alpha V.
Mm.
And so we have written in form of the CL alpha V, which is the
Mhm.
uh, uh, slope of the CL with respect to the side slip angle,
Right.
multiplied by the alpha, which is here alpha V with beta plus sigma, and
Mhm.
QV is the dynamic pressure half rho V square, and
Mhm.
SV is the surface area of the tail.
Very good. Good explanation. So NV is basically the moment and YV is the force. So this force YV is generating the moment NV. And this expression is very simple. The way we write the lift force on an airfoil, in the same manner we have written the side force YV. Okay. And what is happening in this equation? Ripinder, you want to explain the third equation?
Sir, we have divided by Q infinity S, and I think B is the, like
Span
in
of the,
moment we use S C bar. Here
hmm,
B must be the span of the.
right. So that's a distinction here. So when you find the coefficient of moment for lateral and directional stability, you use the span of the wing. And when you talk about the longitudinal stability, you use the what do you use? Mean aerodynamic code, MAC, right?
Yes, sir, got it.
Yeah. So Achyut, are you clear in the third equation what we are trying to do? Akhileshwar?
Just trying to understand.
Okay, I'll help you. What is happening here is, because maybe you're not from aerospace engineering, Vipinder is from aerospace. That's why he understand all of these notations very quickly. Half of rho v square as and CL. So I'm just changing the names of these things. The lift force is being denoted by Y. Half of rho v square is just Q, V, just a V, S of V. CL is being written as CL alpha V times alpha, which is sigma plus beta. So CL can be written as CL alpha times alpha for a symmetrical airfoil. That's what we have done here. So this is the lift curve slope, and this is the angle of attack alpha sigma plus beta. So that's what has happened here. This expression, you are very familiar with this expression in this course, right?
Yes, yes.
Now you understand what is happening here. What is going on?
So the angle sigma and beta are exactly, the beta angle is the side slip angle, and sigma is
Side wash.
okay,
So
side wash.
we tried to discuss this in this right here. Ripinder, would you like to explain what is side wash here?
Sir, actually, I'm not currently familiar with the side wash, but it can be like the upwash or the downwash, we can
It
say,
is
due to the.
exactly that. It is exactly that. There is no difference in side wash and upwash and downwash. See, what is happening here is the flow is being disturbed by the existence of the wings. Okay. So whatever angle of attack from the side, the wing and the airplane is experiencing ahead of the wing, it's not same what his tail is experiencing. So because of these vortices and other things, interference here, there is interference of wing and fuselage body. So majorly the contribution comes from these vortices, okay, in impacting the angle of attack here. So that sigma is nothing but a number of that disturbance. So how do you quantify that disturbance? You just put a number sigma. Okay, so later we will try to understand what this number is, and from experiments we are able to know the range of this number from experiments, not from theory. But in theory we are just saying that okay, there exists a disturbance. The angle of attack at the tail, vertical tail, is going to be different from the actual side slip angle. Now, by what magnitude or by what number, that we can quantify later. But for the timing, conceptually, that disturbance is being quantified as sigma. Okay, that's why we have put it sigma here. Now, in this equation, what is happening is, usually when you write L is equal to some dynamic pressure as and what else, CL, okay, then you divide it with Q S, and what you find is CL. Similarly, in the longitudinal stability case, you defined M as some number, okay, and then you divide it with the Q, wing area, and C bar, and that's what you called C small m, okay, pitching moment coefficient. Similarly, we have defined M N here somehow because of those aerodynamic elements. There is an NV. Now we're going to divide it with the dynamic pressure of the wing, area of the wing, but this time wingspan. That time we had a C bar, this time we have a B. So it's a convention, all right? It's a convention. Whenever you look at the data of an aircraft on internet or anywhere in the community, in the books or wherever in research papers, whenever they specify the number CN, they had found out it by dividing with the span of the wing. Okay, that's a convention. So everybody follows it. So that's how you define CN. And this is the expression. I've written it here. You know the expression for NV. You put it here from here to here. You just substitute it. Now, this number is a special number to quantify the size of the tail. And it's called the, what is it called?
Volume of the vertical tail, sir.
Yeah. Volume of the vertical tail volume ratio. It's a ratio of two volumes, if you can see that. SVLV is a volume and S into B is another volume. Can you see that?
Yes, sir.
Yeah. So it's a ratio of the volume. That's why the name vertical tail volume ratio. So it gives us the idea of how large
I think sir again lost the connection. है ना?
Yeah, even I am not able to listen his voice.
Again, I lost my connection and I'm sharing the screen again. All right. So we were here. Am I audible to you guys?
Yes, audible.
All right. So
So this fraction LS upon SB is actually the volume ratio of the vertical tail to the actual main wings.
right.
Okay.
Yeah. Now we have a tradition of defining the derivatives in aircraft community. So what we do, we derive the differentiate the Cn with respect to beta. And what do we get? Since this number is a constant, this number is a constant, this lift slope is a constant. So we differentiate beta, it becomes 1, and we differentiate this, then we have d sigma over d beta. And this d sigma over d beta number is found out from the experiments or from the properties of the airfoil. Okay, so we call this moment slope. So the number that we were looking earlier, there was a graph Cn, beta, and this was a stable one, right? So this slope is this number, this slope, okay? Slope of this line theta. So the tan theta is equal to this Cn beta, all right? Yeah, so now we go ahead. Now we want to understand the control. Maybe you have already watched the lectures, but I thought we can include some part of the control also. So far, before diving into this particular slide, I just want to understand from all of you. You will tell me bit by bit what you understand from directional stability, because we have introduced the directional stability here. Now we'll go ahead one by one. So first, Achyut, you will tell what do you understand by directional stability and what we have done so far. Can you summarize what we have learned so far? Am I audible?
Yes, sir.
Yes.
Yeah, go ahead. Okay, if you don't want to speak, we can go to Akhileshwar.
So the idea is actually not completely clear to me.
Okay. So were you present in this slide, the first slide?
So this is basically the side slip depiction
Okay.
only.
So whenever side slip exists, what what the aircraft is going to do?
It will try to come back to its course.
It will try to make beta zero,
Yeah.
right? And that is what we call stability, directional stability. Whenever a side slip exists, the aircraft has a natural tendency to make it zero. It wants to head into the air, the relative air. So that is directional stability for us. Okay. So we said that whenever beta exists, the aircraft tries to turn into the into the this relative wind. Now, when aircraft turns, any rotation happens when there is a moment, when there is a torque, right? So how the torque is being generated, we are trying to understand that. And we have already seen that because of the side slip, there exists a force, a side force. That side force, if you take a moment about CG, will generate a moment and will make beta zero. So now we know how to compute the force uh, and moment of a airfoil or a wing, and that's what we are doing here. We computed the force, and with that force we computed the moment, and then we defined the moment coefficient. Because I mean, you should understand the importance of these coefficients. These coefficients are important because you can make a graph like this and discuss. That's why, and we find out that these numbers are actually constant. So they are properties. So whenever you are given data about an aircraft, you're given data about the Cn beta, Cm alpha, Cl alpha, and so on. So these numbers actually characterize the aircraft. Right now, we are characterizing the directional stability things. So this is the slope, and that slope is here. And we have also discussed that which of these slopes make it stable. The positive slopes make it stable. All right. All right. So now we want to understand. Can you deliberately make it rotate along about z axis? Can you make your aircraft deliberately rotate? Am I audible?
Yes, sir.
Yes, sir.
Yes, sir. Yes,
Yeah.
sir. So by using
So
the rudder, as it is
yeah,
shown.
exactly, exactly. Now the question is, if I change the rudder angle by some amount, how much the aircraft is going to rotate? I mean, input is the rudder angle, output is the rotation of the aircraft, but by what magnitude? How much? That is the question, right? So to quantify that question, to answer that question, we have to quantify how much torque or moment the rudder is going to generate. All right. So that's why this slide. So what is happening here is, all right. So you define the moment similar as earlier, LV times YV, and this time you take a negative sign. Why is that? Okay, we'll come to that later. Just follow along, because the answer lies slightly later. Okay, so it doesn't matter which way you would. Okay, it matters, but it is sign convention. Remember. So with respect to the rudder angle, uh, what happens when the rudder angle is positive, when the rudder angle is negative, and keeping that thing in mind, this angle is defined. But for stability, that number was taken as positive, but now we have taken it as a negative, and there is a reason for that. So just let's go ahead and substitute the YV. Uh, Anyone has any doubt about the expression YV, where it came from? And what does the quantities mean?
No doubt, sir.
Uh, Akhileshwar, you have any doubt in the expression YV?
No, no. In this expression, it's clear.
Yes, very good. This is just the lift slope, dynamic pressure, and the area of the vertical tail. And that becomes the side force. When side force is multiplied with LV, you have a yaw moment. Then what you do, you divide with the dynamic pressure at the wing, surface area of the
Sir,
wing.
LV is exactly the distance of the vertical tail, or
Yeah. So let's go back and show you what LV is. Okay. It will be much clear here. This is the CG of the aircraft, and this is the force is perpendicular, the force YV, and this distance is LV. So when you compute,
yeah, now clear.
yeah, when you compute a moment about this point, then this is the LV.
All right.
All right. So we normalize it with QWSB, and we obtain the coefficient just like earlier. And what happens later? We simply substitute this expression LV here. So we have a QV, LV, SV. This quantity already have a name, the volume ratio. Now, something else happened here.
Sir, actually, the doubt that I was getting here is how LV into SV is giving us a volume. Means which kind of volume are we getting from it? These.
Okay. So you're right. It's not anything directly related to the aircraft and its volumes. It's just a volume in dimension. There is a area, there is a length. Okay.
Okay, just because the length is going to the power 3, so it's becoming a volume.
Right.
Okay, okay.
Yeah. And also this volume, these two numbers, they quantify the properties of the vertical tail, right? And these two quantifies the properties of the wing. So we just call it volume ratio for the vertical tail.
All right,
So
sir.
here is
Got
this
it.
number. Yeah. So what is happening here? I mean, I understand everything, but I don't understand this bit. Can anyone explain me this bit? What is happening here? What is this number? Rupinder, can you help me understand what is happening in that box?
Sir, it is like in that of a case of for that I studied in for pitching movement.
Mhm.
It is the, I can say that the slope for the DCL V, which is for the rudder, upon the deflection angle multiplied by the deflection angle. Like D deflection angle is the denominator, differentiated.
Okay. I'll try to explain what he has just said. See, we have this number CLV. We need to quantify this number, right? And what happens when you change the rudder angle is the question. Let's say this is the top view of your vertical, and let's say this is the rudder. Now, rudder is probably not deployed in this picture, but it is deployed in this picture. And if you measure its angle from this code line, there is some angle delta R, right? Rudder is being deployed by some angle. Now, what is happening here? When you deploy the rudder, this whole thing, it's sort of a wing, right? It's a wing because there is an airfoil and something like a flap. Now, what is happening here? It's experiencing some flow with a velocity v at a certain angle of attack. Now, when you deploy the delta r, what changes in terms of aerodynamic properties of this? Its CL changes, of course. Its CL changes. The CL it is experiencing. I mean, let's say there is a lift, there is an airfoil, and when you deploy this device, so the overall camber of this aerodynamic element changes. Do you feel comfortable with this idea? Let's say there is no surface at the back. This is just a simple one piece, and the velocity is coming at certain angle of attack, and the CL has some behavior, some property. But now, since this structure is in two parts, one part is rigidly fixed with the aircraft, but one part is free to rotate. So when you are able to rotate it at different angles, what happens to this curve? Let's say this is CL and this is the angle of attack, and let's consider a symmetric airfoil case. So this is one case. Now when you deploy this aerodynamic surface at the back, in our case it is rudder, what happens to the CL graph here?
Sir, the lift CL value will increase of for this, and
Hmm.
the graph will shift a bit up.
So basically it's becoming cambered, right?
Yes, sir, it is giving it camber.
Yeah. So we are changing the camber of the wing here fundamentally. So the idea is when you deploy the rudder, the properties of the whole thing, rudder plus the vertical tail, it changes. Now, how can you quantify that? You quantify that with a derivative. You find out the derivative by from data, of course from data, but theoretically I can say that you differentiate this CLV with respect to the uh, change in the rudder angle, and then you multiply with the rudder angle, and ultimately what is that you get this quantity CL. You are simply differentiating DCL with respect to the rudder angle, and then you multiply with the rudder angle. Then what is the overall quantity? You simply get that CLV, right? Anyone has any disagreement here? No? Okay. Here is the question. Maybe you did not get the idea. So this is y, this is x, this is one line, this is another line. This line has a slope m1. This line has a slope m2. I want to find out the values of y for both of these lines given x is equal to x naught. So what is the value for y for line 1?
Can we use the formula y is equals to mx plus c here?
Not just can we have to. That there is no other way. Okay. So what is the answer for y?
Sir, y here it will be y is equals to m1 into x, sir.
Very good. Y1 will be m1 into x naught, right? Y2
Yes,
will
sir.
be
Y2 will be m2 into x naught, sir.
m2 into x naught. Absolutely correct, because they are both passing through the origin. Now, what is m1? How do you define m1? Some who has understood geometry or have taken some classes in geometry, they know it is dy by dx. It's the slope. All I'm
Yes, sir.
saying
It
here
is the
is
angle made by the line line m1 with respect to the x-axis, sir.
right. Now, what happens if I just change the name of the variable? I make delta r on this line, CLV on this line. I find out the slope somehow. So what will happen? The slope is this dCl over delta r, d delta r. Now, if I want to find out the value of the CLV for a certain delta r, all I have to multiply is delta r. This is the slope, and this is CLV. Now I think it's clear, right? Why it is written like this here?
Oh, sir, so you mean to say that you're comparing this equation with y is equals to mx plus c?
Yeah, it is exactly that. Okay.
Okay, sir.
It's exactly that. Now the thing is, we can find this number from experiments. See, in a wind tunnel, you can change delta R 1 degree, 1 degree, 1 degree, and you can find out the data for CL, and then you simply take the derivative from the data. So you have the slope. So this number can be quantified from experiments. So in theory, we are saying that, okay, we describe this quantity in this manner, CLV. And why do we do that? Because we are going to change delta R. So we want to quantify the effect of that. So when delta R changes, how much CLV changes? We need to find that derivative. So we express deliberately in terms of the derivative here. So now I think it's clear why CLV is written like this. So this expression is also clear. Now, the name of this whole quantity is Cn delta R. Slope of the Cn with respect to delta R, because when you multiply delta R with it, you get Cn. So definitely it's the slope, right? I just explained it.
Yes,
So
sir.
yeah, then it's the slope. All right. What else we have? Yeah. So it's the same equation here. Okay. And now the question is, how do we find this number? So there is one simplicity. We can do one thing. We can differentiate CL with respect to alpha, and then we can differentiate alpha with respect to delta R again. And this number is already known to you. How? Ripinder, would you like to explain how this number is known to us already?
Yes, sir, from the graph, sir.
Yeah, because whenever you have an airfoil, you know it's CL alpha graph, right? It's the CL alpha. This is the CL alpha. Isn't it CL alpha? This is CL and
Yes,
it's
sir.
yeah, it's the CL alpha. How do you find this number? From the table,
Sir, in
from
the
the graph.
wind tunnel, sir, we can test it for
You're
different
right.
reasons.
You're right. You can test things, but our life has been made easier. How? All we have to do is look at this graph. This graph is given in many of the books. So it's coming from experiments. I 100% agree with Rupinder that you do experiments and find out. But since you are a designer and you don't have access to aerodynamic testing always, so what do? You look into the literature and find out, is there any
Historical
connection?
data, yes, sir.
Yes. So the connection has been found. So the connection is, if this is your main control, main lifting surface, and this lifting surface has a secondary surface that you can deploy, you have to find out the ratio of the area. So let's call this area as A1, and let's call this ratio as area A2. So A1 divided by A2 is known to you. So when you design a vertical tail, you design this ratio, you choose this ratio. Like your rudder area should be this much in comparison to the vertical stabilizer that you choose. So you know this from geometry of the design, and it is approximately 70%. So the control surface is this, okay, and this is the lifting surface. So the control surface is almost 70% at max, okay, and usually it's 20-30%. So when it is 20-30, you can just look at this graph and find out this number. This number is given as tau, okay. So this tau is available from this graph. So notice that this number depends on the ratio of the control surface area and the lifting surface area. Which area we are talking about? Do you guys understand which area we are talking about? Is it
We are
the
talking about vertical tails, sir.
no, the cross section area or something else? I am drawing cross section area, but please don't understand it's cross section area. It's the area of the entire thing. Let's say, yeah, this is the area I'm talking
Area
about.
of the whole surface, tail surface.
Yeah,
It's a surface area, sir.
exactly. This area. So this is the lifting surface area that I'm right now annotating. Okay, and this is the control surface area, the rudder area with cross. So you take the ratio of these two numbers and you find out this tau. You put it here. How do you find this number? You already know the slope of the uh, the airfoil that you have chosen already for this uh, vertical stabilizer. And usually it's 2 pi. If it's symmetric airfoil, you can just choose 2 pi. You can take a ratio. So you know this number. How much lift of this surface will change when you deploy the rudder by a certain angle. The delta R is in radian usually, also in degrees. So the data is given with respect to degrees and radians both. And now if you know these numbers, you can generate how much yawing moment will be generated on the aircraft. And if you know the inertia about z-axis, you can tell how fast the aircraft is going to rotate using Newton's law. Okay, so the flight stability and control are directly connected to the flight dynamics. We are generating forces, moments, and those forces and moments are going to turn and rotate the aircraft somehow. We can quantify those moments now when we know the properties of these surfaces. All right. Now, what we have got in the store. Yeah. Why do we need directional control is the question. Why do we need the rudder? And these are 4 situations where rudder is of utmost importance. We can actually work without rudder in most of the cases. In fact, we can yaw without rudder. Anyone wants to explain to me how can we yaw without a rudder?
So by
So using
banking,
roll,
using the ailerons,
yes, sir, roll control.
Absolutely correct.
roll.
And you will be surprised that rudders are least used control surfaces. They're not really used until you need them. You absolutely need them until you absolutely need them. Whenever aircraft is
Yes, sir,
flying,
that is true.
the pilot is going to use ailerons for yawing and for rolling and pitching up, pitch down for elevator. Now rudder is always useless. Most of the time it's useless, but it's useful in these 4 situations. The first is adverse yaw. I mean, you can read it and just explain to me what it is telling to you. I won't explain. You explain to me what is adverse yaw.
Sir, adverse yaw means that, as you said, sir, ailerons are used for most of the time for turning movements, sir. So
Right.
here the aircraft is flying slow, sir. So when we use try to use ailerons to move towards one side, sir, the ailerons, okay, they'll give that movement to turn towards that side, sir. But they'll create an opposite force to equalize the force which we are applying on it to yarn, sir. So here to overcome that adverse yarn, the rudder has that moment and capability to overtake that adverse yaw and turn it to the direction in which we want the flight to move.
Yeah, you're right. So the thing is, when pilot is banking the aircraft, okay, so let's say you bank to the right. I mean, the right wing is going down. So you bank to the right. I'll show you the photograph also, what it means to bank right. Let's say this is your airplane and you bank to the right, which means like this. Now you are supposed to rotate in this direction, right? You're turning in this direction. You are going straight, you're turning in right direction. But what may happen is, now it's not easy to explain why this happened, because it happens with aircraft and
Pardon, sir,
it's
what
not
are
visible
you,
directly. Hmm?
sir, what are you saying?
Like my voice is not audible or not?
Sir, to me, it just cut it for a bit.
Okay. Now I'm audible, right?
Yes, sir, you are now.
All right. So what I'm saying is, if let's say the aircraft is banking to the right, Okay. So one component of the lift is acting like this. Let's say this
Sir,
is the
are you
lift.
explaining why there is a yawing movement due to rolling?
Yeah.
Sir, can I answer?
Go ahead.
I read it, sir, in the book, sir, that when we for like roll to the right direction, the
Mhm.
right aileron is deflected upward, and the left aileron will be deflected downward. So
Mhm.
the upward aileron will generate drag, sir.
Mm.
So the drag will
Absolutely.
there is a increased drag here and a decreased drag in the left direction.
Mm.
So due to this well, unbalance of forces, the airplane will try to yaw in
Yep.
the direction of the roll as well.
No, no, opposite of that. So what will happen is you are banking to the right, but your aircraft is yawing to the left because of that drag force. Okay, and this is called adverse yaw. To stop this adverse yaw, you deploy the rudder. So one requirement for the rudder is to counter the adverse yaw. Second one, I think it's pretty easy to understand. Anyone wants to explain?
Yes, sir, craft landings, these are called.
We want to hear from Akhilesh now. What are crosswind landings and why rudder is useful there?
So crosswind landings are actually when an aircraft is coming to land on an airstrip, the winds are perpendicular to the direction of landing, like kind
Right.
of.
And what happens in
So,
that case?
so actually the plane will start getting adverse yaw kind of thing because the
Not
situation that
adverse,
was
but
coming of
yaw. Yeah.
side slip
Basically,
conditions will kind of appear.
yeah, you can directly say it will disturb the alignment with the runway. Okay. It will rotate it left or right, which way the wind is coming. Okay. So
Yes, sir.
to counter that, you need a rudder. The
Sir,
third
actually,
one,
we can understand it as like if the aircraft is coming on the airstrip and we have
mhm,
crosswind, so it's actually the condition of side slip already. Like the
exactly,
direction of wind is already at an angle beta.
exactly, and the aircraft will turn towards that, towards
Hmm.
making beta zero, right? Yeah, absolutely
Hmm.
correct. And the third thing, Achyut, you would like to explain asymmetric power condition?
Yes, sir. Can you give me 2 minutes, sir?
Yeah, yeah. Read it.
Sir, I understood it, sir.
Tell us.
Sir, it means that, for example, we have a twin engine aircraft, sir.
Mm-hmm.
So in that, one of the engine, due to some reason, it fails, sir, and the aircraft is flying at low speed.
Okay.
So because of this, what happens is that, for example, the right one fails, sir. So
Mm-hmm.
the left one will try to push the aircraft towards the right side, sir. Like it will be trying to push the aircraft towards the right side, or we.
Can you see the screen?
Yes, sir.
So this is what you're saying, right? One of the engine fails, so there
Yeah,
will
yeah, yes,
be
sir. Yes, sir.
there will
It will
be
try to create a yawn
mm,
in the opposite direction where the engine is there, sir.
yep.
So, in
That's
order
already.
to overcome that yawn, sir,
Mm,
we need to have a rudder powerful enough to overcome that yawning movement, sir. So that even if one engine fails, with the help of another engine, we can carry out the flight, sir.
right. And how about spin? Uh, Rapinder,
Yes, sir.
what is spin recovery and how rudder is useful?
Okay, sir. So spin is a condition in which the aircraft loses its altitude and goes into a spiral vortex down,
Mm-hmm.
nose down. So so rudder is given in opposite direction to the we can say the spin, so that the spinning movement will slow down, and then we can level the wings and pitch up to climb out of the.
Exactly. So rudder is required to be powerful to get us out of the spin. So other two of you understood what spin means. He meant something like this.
Yes, sir.
The
So
aircraft
like we
behave.
are, yeah,
So
Yes,
we
sir.
are
Just
turning
want
and
to
losing altitude,
exactly
yawing continuously and losing altitude and going down,
right.
like a
So
kind of tornado.
right. So those turning thing has to be stopped by using a powerful rudder, and then you get out of this spin and then fly wherever you want to. Okay. So this is it for today. Maybe I could have covered roll stability as well, but now I'm
Yes, the
feeling a little
role
tired.
was it.
So I'll discuss role in the next session, and I have given you 2-3 questions that you can answer. All right. So
Sir,
Sure.
yeah.
last week you gave an assignment to me, sir, to speak about reflex aerofoil, sir.
So you hold on for today.
Yes,
And
sir.
this
No,
is
I am not
ah,
saying, sir.
mhm.
I tried to find everywhere, sir, in Google, sir, but I'm
Okay.
not able to get an appropriate information about that, sir.
Okay. So
Because
then we can transfer this assignment to Ripinder then. He's from aerospace also, so he can maybe explain to you in the next session. So Ripinder, your workload is that you will explain to him what reflex airfoil is. Okay. You can make a PPT of 2-3 slides and just present to all of us. All right. Is he hearing us or is he feeling? Am I audible?
yes, sir, you
Yes, sir,
are
you are
audible.
Yes,
audible.
Okay. Okay. Maybe we lost his voice, but nevertheless, uh, if he explains you, then it's fine. Then I'll explain you in the next session. Okay.
Yes, sir.
Yeah. And then we'll stop today. You guys can leave the meeting, and then the meeting will end.
Okay, thank you, sir. Thank you very
Okay.
much.
Thank
Yep.
you, sir.
thank you, sir.
Yep.